Hello class. Today we are going to talk about mechanical systems when we do have initial conditions. So our last example, we said that our initial position and our initial velocity were both 0. Now let's see if they have some value. So we're going to still talk about our mass spring damper system. So we've defined which direction x is in. We have this governing equation. So that's all going to stay the same because those are part of our system parameters. We're also going to keep the same mass spring damper values, but we're going to say that our input force is 0 and that we have an input position of 2 meters and an input velocity of 1 meter per second. So the system has not changed, but the inputs affecting the system has. So let's take that governing ordinary differential equation, and first step to solve through a Laplace transform would be to take the equation, put it in the Laplace domain. And we can go ahead and do that. Because we have initial conditions, we're going to include those, and then we can go ahead and put in those values that we've assigned, because in order to assess it further at this point, we need more information about the system. Eventually, we're not going to have to put in the variables or the inputs, and we're going to be able to treat that at a later point. If we put in those input values, numerically solve it, then we can start to isolate our unknowns. That's actually step 2. So let's go ahead and write step 2 because I've gone ahead of myself there. And we isolate the unknown variable in the Laplace domain. So we can have that as x of s is equal to 2s plus 11 over s squared plus 5s plus 11. That should be 5s plus 6. Let's see if I can... Yeah, nice. So s squared plus 5s plus 6, because we're just taking this component here and putting that in the denominator and the stuff on the right, putting it in the numerator. So it got a little messy there because I did not expect to have to write 2s plus 11 s squared plus 5s plus 6. Now step 3 is we're going to simplify the forms using partial fraction expansion. So we take that equation, I don't know why I just wrote it again because we're going to have it, and we want to split it apart. Same equation from before, we know it's going to be s plus 2, s plus 3, but if it wasn't that obvious, we could use the quadratic equation. So quadratic equation in song format is s equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And a few years ago, my students begged me to never sing that again during class. Technically, this isn't during class, it's during a supplemental video, so I got outside of that promise. And so in this case, b is 5. B squared is 25 minus 24, so we have negative 5 plus or minus 1, which gives us negative 6 or negative 4. Divided by 2, we have the answers of negative 3 and negative 2. So those are the values of that equation that set that equation equal to 0. And we can go ahead, tell ourselves that x of s is going to be 2s plus 11 over s plus 3, s plus 2. And I'm just trying to come up with some variable names, so I'm just going to say n1, n2. And we know that if we combine them back, we would have n1 times s plus 2 plus n2 s plus 3 is equal to 2s plus 11. Because we'd have to multiply, and let's again just write some extra. We're just saying that if we wanted to combine the fractions, we would multiply each fraction by 1, and the format 1 would take, in the first thing would be s over 2 plus s over plus 2, or s plus 3 over s plus 3, and that's how we get that equation n1 s plus 2 plus n2 s plus 3 equals 2s plus 11. I'm not going to explain this through every time, but I figure we're early on in the semester, let's try to explain things a little further. And you can go ahead, press pause on the video and try to find the values of n1 and n2 yourself. Again, you could do that by saying n1 times s plus n2 times s is equal to 2s. 2n1 plus 3n2 is equal to 11, or you could set 2 equal to 0, s equal to negative 2, or s equal to negative 3 to isolate your n1 and n2 terms. Either way you do it, you should come out with n1 is equal to negative 5 and n2 is equal to 7. So that tells us x of s is equal to 7 over s plus 2 minus 5 over s plus 3, or you could say negative 5 over s plus 3 plus 7 over s plus 2. Hopefully you know that's the same thing. And now we have simplified our terms, which will bring us to step 4. And step 4 is going to be, let's use those terms. We're going to use the Laplace transform table to go back to the time domain. I didn't have the Laplace transform table handy, and my iPad did not want to connect to the internet when I was making this, so we're just going to write that from memory. The Laplace transform of e to the negative at is equal to 1 over s plus a. You don't have to have that memorized. You're always going to have a Laplace transform table on the screen or on a paper. But we can go through, say, x of s is equal to 7 over s plus 2 minus 5 over s plus 3, which brings us to 7e to the negative 2t minus 5e to the negative 3t. And so we now can predict x for all values because we have those input information. So if we compare the two examples, the one from the previous video and this one, in both cases we had the same system. So the systems that were the components that reacted in a non-trivial manner. But we changed the scenarios between them. So in the first one, we had zero initial conditions, but we had an input impulse force, and we were able to say that x of t is equal to e to the negative 2t minus e to the negative 3t. And in the second scenario, we had initial conditions but no input force, and we saw that our output was 7e to the negative 2t and minus e to the negative 3t. So in both situations, we have the same terms showing up across both scenarios of that e to the negative 2t, e to the negative 3t, but the value across them changes. So we're going to see some more patterns and talk about how we can set up systems without knowing the initial conditions or the inputs at the start, but how can we see what's consistent for our system in the next video. I'm sure you're just waiting in suspense. So I will go ahead and start writing those notes down. Okay.